We didn't have time to get to the D problem, but let me explain a little bit about what that problem's talking about. If we get a wave propagating and simple harmonic motion at this end, so that simple harmonic motion kind of propagates down the wave, we get a nice smooth sine or cosine wave in space. Now that wave propagates on. If it gets to the end of that string, and that string is attached to something really solid, then that wave is going to reflect back in a way that we'll see when we go a little deeper into the actual mechanics of the wave. But the wave is going to reflect back. Now, if the peaks of that wave are timed so that they correspond to the peaks of the wave that's coming down, so if the peaks of the reflected wave and the peaks of the propagating wave match up in a certain way, and again we'll see exactly how that works and what that means, you get what's called a standing wave. So that, for example, if these are the two ends of the string, you could have a standing wave where here's a wavelength, but the string here is oscillating between here and here. At the same time, the string over here is oscillating from here to here and back. These oscillations will be out of phase. When this one's up, this one will be down. When this one's down, this one will be up. But you're going to get this resonating standing wave. Okay? The condition for a standing wave is simply that it's stated a little differently in the problem, but I'm going to state it differently right now so you have at least a couple of ways of looking at it. The condition is simply that the length of the string be a whole number of half wavelengths. Okay? So here, the length of the string, assuming the string is attached here and here, the length of the string is 2 half wavelengths, 1 complete wavelength. This is also possible. The length of the string is 1 complete wavelength. Here's another possibility where the length of the string is 3 complete wavelengths. So that might help clarify what the question is talking about. By changing the tension in a string, we change the speed of propagation. If we continue oscillating at one end of the string at some frequency without changing the frequency, then that change in the velocity of propagation is going to result in a change in the distance between peaks. If that distance between peaks matches up with the length of the string in a way such that the length of the string is a whole number of half wavelengths, then we can get a standing wave.